Okay, so polynomials. We talked about what a polynomial was the other day, right? Explain to me, somebody just quickly describe what's a polynomial. What, say it again? One more time. X to a power. Okay, that's part of it. That's a power function. But a polynomial, poly means many, nomial means terms, right? Okay, so we got a bunch of terms, and really the way that we define what a polynomial is we just define what each term would look like, right? It's just a sum of terms, and each term has two parts, and what are the rules? What are the two parts? Okay, well, if it's multiplied by 0, that term would disappear. You're right. Okay. So, okay, there's a coefficient, and then there's a power function, right? There's a coefficient and then a power of x. So the coefficient, what are the rules about the coefficient? What kinds of numbers could the coefficient be? All reals. Could be anything, just can't be, it can't be a complex number with an imaginary part, but otherwise anything's fair game. What about the exponents? They positive what? Integers. Okay. What else? There's, so for example, we could have something like this, right? Pi x to the fourth. So that's as much as I could do then, because I've got positive integers for my exponents, right? Because that would be a 1. Okay, or 0. How do we say that's set? Because I could also have something like that. What's the power of x there? X to the 0. I wouldn't write it. Just like I wouldn't write that 1. It's implied, but there is an invisible x to the 0 there. So then what's the set, going back to algebra 1, that includes 0 and then all of the positive integers? What do we call that? A lot of these sets are kind of, we don't use them very much. Like, how many times do you ever use the natural numbers? 1, 2, 3, 4, etc. You almost never even say that set. But this is one we use quite a bit. The positive integers plus 0. Let's play a little, what's this little hangman here? We're playing a little hangman.
Oh,
Come on now.
I always just like the
Give you an A?
We really know A. Wrong numbers.
What?
E. Whole numbers.
Ah, there it is.
No. Come on, we're gonna go for like 20 minutes.
Oh, Emma.
That's what was my plan too. Yeah. I'm just gonna get some numbers like 1.
Okay, so exponents are whole numbers. If we write a polynomial in standard form, what does that mean? But I mean, what's that mean? Is that in standard form?
Yes.
It is. How come? Okay, because the exponents go from largest to smallest in descending order, right? What's the degree of that polynomial? What did we say the degree of the polynomial is? Okay, it's quartic, yeah, but we just usually would say a number. So it's, what's the degree going to be? 4th degree, because that's the biggest power of x, right? That's significant because when we look at the end behavior of a polynomial, how is that related to the degree? Remember we looked at that, we zoomed out on that picture and it changed its behavior a whole bunch, but it ended up with what? X to the 4th, yeah. So the leading term, right? The leading term is the term that determines what the end behavior is going to be in the polynomial. So we call that the leading term. And what's the leading coefficient in this case? Pi, yeah. Okay. So there's our brief review. I've been starting with this semester, I've been putting all of the PDFs up from our online textbooks. You don't even have to log in. You just, I mean, they're just PDFs in Moodle. You probably want to be just glancing at that stuff. I don't think you need to spend a lot of time with it. When we cover, I'll kind of tell you when you do. Like for example, on these two things we're going to cover today, I don't think you need to even look at the book at all. But there is some stuff coming up. When we get to dividing polynomials and the binomial theorem and some things, then I think you have to lean on that textbook resource just a little bit more. One other thing about this, and then we'll move on. So this is in standard form. What's another form in which we could write a polynomial? Factored form, yeah. Our book calls it intercepts form. Why might they do that? Like if I were to write a polynomial out, let's say we have p of x equals something like, obviously factored form makes sense because it's factored, right? What about, why might we call that intercepts form? Okay, because if I were to set it equal to 0, now what?
Make one of the factors equal 0.
Okay, so then it's easy for us by applying the zero product property here. If I set the function equal to 0, what am I really doing, right? That's just y, isn't it, right? So by setting p of x equal to 0, and we'll usually put it on the right side. That's just our, that's kind of almost a custom we have in math. We want to put the 0 on the right. But we set up an equation here that's going to allow us to solve for the values of x that make the function 0, right? Well, where is the function 0 on the xy plane? Yeah, the x-axis, right? Well, the y value is 0 along the x-axis, so these are just the x-intercepts, right? Okay, one other thing I was thinking I wanted to ask you about. Let's say we wanted to, factor something like this. Let's say I'm just solving this equation. What would I do to that? Okay, yeah, right. First thing I always want to do, remember, is I want to always try to factor out the greatest common factor, right? So I could undistribute a 2x here, right? Okay, what am I left with if I factor out a 2x? Plus 5, okay. How'd you get that? Somebody raise your hand and tell me. There's a couple ways you can think about this, but I want to make sure everybody's in complete control of that process. Well, you divide. Okay, so Ruby, you're saying I could divide what to get x squared? 2x cubed divided by 2x, right? So one thing you can say is that factoring is a process of division, and it always is. It's easy to see when you're factoring out a greatest common factor, right? What I'm left with in here is what I'm going to have when I divide the original by 2x, right? Does that make sense? It's the very same thing, and I really, we haven't spent a lot of time talking about this, but what if I want to factor a number? What if I factor the number 6? What do I get? 2 times 3, right? And we can include the 1, I guess, but if we, 1's not necessarily something that we need to have there, right? But the 2 and the 3 are the prime factors of 6, right? Okay, well, how do I get the 2? Yeah, I divide the 6 by 3, don't I? Right? So it's the same thing. It's the very same thing. These two factors, this little guy, this little monomial factor, and then this trinomial factor, when I multiply those together, I get the original, right? So it is a process of division, technically. But the other way you can kind of think about this, in a practicing way when you're doing the math, and this is how I do it a lot of times, I'll just say, okay, well, 2x times what is 2x cubed? 2x times what is 4x squared? 2x times what is 10x? Right? Make sense? Okay, questions? Okay, quick recap. All right, so the topic of the section 6.1 is adding and subtracting polynomials. What do you do when you add polynomials? Add like terms. I mean, that's done. That's all I'm gonna say about it. Add like terms. There's nothing else to say really, right? I gave you a very short assignment. I did put a couple word problems in there that are really simple, but I want you to just kind of think about math contextually a little bit. So We're done with adding polynomials. Subtracting polynomials, almost as easy. What if we did something like this? What would I do? Okay, combine like terms, yeah. But what's probably, we think about this in terms of an approach. What would I do there? Distribute the negative, exactly, and then what? Combine like terms, then add, right? Done. We're done with subtracting polynomials. I don't need to say any more. You guys will be fine. Multiplying polynomials, you also know how to do, but I do want to show you maybe two different approaches to multiplying polynomials. What if we want to, for example, let's just say we want to multiply what if I want to do that? How might we approach multiplying those polynomials? Really all it is distributing, isn't it? Right? So I'm just going to distribute from one polynomial over the other, we'd say in math. Does it make any difference which one? Let me make one little tweak to this. Very tiny. And it's not like this changes things in such a tremendously profound way, but there's one thing, I've got a little bias here that I'll tell you about. When you distribute, how would you distribute on this one and why? Not that it's a really big deal. I think it makes it a little simpler though. You're a little less apt to make a mistake if you choose one order of distributing over the other. What do you think? Should I distribute the first polynomial over the second one or vice versa? Yeah, I don't know that there's a right answer. My bias is I would always count the terms, and the polynomial that has the least number of terms, that's the one I would distribute over the other one, because it seems like then it's a little bit less confusing. And when you, maybe this will make more sense when we go through these two processes, but for example, when we stack things up vertically, then you have 3 rows instead of 4. And so, I mean, you don't have to do it that way, but I just have a sense it's a little bit easier to do. So all we would do then is, and I don't even think we'll just start the process and I don't know if we even need to finish it. I would take, for example, the 3x squared and just distribute that one all the way through, right? And get what? (12x to the 5th), good, okay, plus, minus, right? Minus, plus. Okay, and I could keep going with this, right? If I distribute the x, that's going to be easy. Distributing an x through a polynomial just does what? So, okay, so it's just going to add 1 to the power of x. And if there is no x there, 0 goes to 1, right? So it really even does the same thing there. So I take the x, and I distribute that through. Now, what are my options here? Well, I could just continue. We'd call this horizontal multiplication if I just write out a long string of terms. And I won't even finish it, but I'll at least add a couple of them. I'm going to get, what, 4x to the 4th plus x cubed minus 2x squared plus 7x. And then I would have to keep going with distributing the 4, which we won't do. When I'm all done with the distribution process, what would be the next step? Okay, add like terms, right? Here's one little thing you can do that maybe makes life a little bit simpler there. When I add up the like terms, as I go through and look for like terms, it can get a little bit confusing. And so if I'm adding or if I'm multiplying polynomials horizontally, what I always do is I cross them off as I go. Right, so then you don't have to look for those anymore, right? So that'd be 7x to the 4th, etc. Negative 6x cubed plus x cubed is what? See it? 5x cubed, okay. Right, and then you just keep on going down the line. And that's fine, it works, but what's the disadvantage of that technique? It's easy to get lost, you get a long, long row of terms, right? Any suggestions as to how we could organize that a little bit?
Do it vertically, place, the second polynomial underneath the 3x to the 4.
Okay, good, so we could, instead, we could add up all the like terms vertically, and that's the way I always like to do this. So for example, say we had something like this, say we had okay, so how might that look then? If I distribute the 4 through, what am I gonna get? Okay, so, 12x to the, you know what I wanna do? Let me do one little thing here I wanna do. I'm gonna do this. Okay.
Your assignments too.
No. Okay, next.
No.
Plus. Okay.
Minus 20x to the 4.
Okay, does that seem like a good way to do it right there? Anybody see any potential problems with what I just did?
Coefficients.
Say it again. Might get the 4th confused with the 5th, and when I distribute the negative 3x squared through, what's my first term gonna be? Negative 6. X to what power?
Wouldn't it be 9x?
Oh, sorry, 9, my fault. 9, it's 9x to the what? To the 5th, what's wrong? There's no 5th, so what should I always do when I'm using vertical multiplication? I gotta leave a column for each power of x, even if it doesn't show up the first time through, right? That's really important to do. So you get the idea, right? So then, and I won't go through the whole process again this time either, but if that's my x to the 6th, I gotta leave a space for the 5th, and then where were we? Minus 20x to the 4th, and now if I distribute this guy through, there's my minus 9x to the 5th, right? Minus 21x to the 4th, etc., right? See what I'm saying? And then when I add up, how many rows am I gonna get? 3 rows, and then I'll just add vertically. It makes things a lot easier, right? But you gotta leave a column for each power of x. And we'll do stuff like that for the rest of the year. Preserve a space just in case. All right, so last thing I want to show you here, this is not really a huge deal, but it's just something that I think is kind of cool. I want to just kind of show you that sometimes you can model multiplication of polynomials in a way that geometrically that makes sense, right? So this really just represents, this little picture just represents the product of the polynomials x plus 3 times x plus 2, right? Now what happens if I expand that out? What do I get if I distribute? So I'm going to get x squared plus, yeah, I'm going to get a plus, I'm going to get a 2x plus a 3x, which are going to combine to 5x, right? And then plus 6. Do you see how that pertains to the picture on the left? Right? Of course, if this distance is x plus 2 from there down to there, and this distance from there to there is x plus 3, well then the rectangle, that creates a rectangle, right? length times width. Okay. But if you break this up into subspaces, well, it really does break it up into a series of rectangles that add together seamlessly to create the big rectangle. If you think about kind of subspaces or sub areas of the whole area, right? See that? Okay, pretty easy to see here, but you can extrapolate that up to 3 dimensions also. So let's look at this guy. If I want to multiply together the 3 polynomials, x plus 3, x plus 2, and x, well, we can represent that 3-dimensionally as a rectangular prism. That's x plus 3 by x plus 2 by x, right? And we can do the same kind of thing. Right, we can break this up into 4 separate volumes that we could add up. If I were to multiply this whole thing out, well, what am I going to get? We can do this pretty quickly. How would I probably, well, what would I do? So I could distribute the x. I've got this, look right here, I've got this x plus 3 times x plus 2, right, that we just did. And what did that give us on the last page? X squared plus 5x plus 6, right? Okay, or times x, right? So if I distribute the x through, then I'm just getting x cubed plus 3x squared plus 2x squared plus 6x, right? And what do you see down here? Right? X by x by x, there's the cube, that's x cubed, right? There's the 3 by x, that's the 3x squared. Back here in the corner, it's going to be, see there's that extra 2, so it's 2 by x, so my 2x squared. And then finally, that guy in the corner, that's 3 by 2 by x, so it's my 6x. See that? I just bring that to your attention, not that it's anything so super profound, but a lot of times you can do stuff like that. You can take a product and you can represent it geometrically. You know, each of the terms in the polynomial ends up having some geometric meaning in this product. Now it gets a little tougher. What would be the problem if I did this? Oops, gosh. What if I did this? Now what's the problem with representing that geometrically? Yeah, it's 4-dimensional, so you have to go ask some other creature in a different universe what that one looks like. But if we, here's the thing though, if we could see what a 4-dimensional space looked like and it would make sense to us geometrically, it would still work. We just can't, because we only have 3 extended dimensions in our universe. But other universes might be different. I'm sure they probably are. If you agree with multiverse theory, there's 100% certainty that they do. Yeah, question?
Oh, no.
Oh, okay. All right, so, how much time we got? A little bit. Oh, we got quite a bit, don't we? We got 17, let's see.